Good morning. Is everybody awake? Thank you all for coming out this morning. It's never the easiest time to be dragging yourselves out of bed and coming along to a presentation. I've done my part by wearing a shirt that should wake you all up. That's my intention. In any case, we've got some great speakers this morning at the SDN applications session. I'll ask you first off to put your mobile phones on silent, if they would ring anyway, inside this giant Faraday cage that we're sitting in. Our first speaker this morning is Eduardo Jacob. He's going to do a presentation for us called Deploying a Virtual Network Function over an SDN Infrastructure. Eduardo, after a fairly varied career in public and private enterprise, is at the University of the Basque Country, where he is acting head of the Communications Engineering Department and leads the I2 Research Lab. His interests are focused on software-defined networking, hence the talk today, across a wide range of topics such as security and so on and so forth. And part of the way into it is taking the daring step of having his associate there, John Matthias, joining him for a demonstration, which I'm sure will go very well.
Yes, we think so.
So I'll hand over to you now, Eduardo. Thanks.
Thank you. Good morning, everybody. Thank you for coming so early in the morning to this presentation. We will present work that is being done in our university, in our laboratory, and which involves an OpenFlow infrastructure which is in operation that we had already explained some time ago. This is the agenda. I will try to go through it to arrive in time. I also would like to explain you that we will have to leave as soon as we finish the presentation because we have to take a plane. So if there are any questions that fit in the time frame, it's okay. If not, you are always welcome to send me questions by email. Well, the OpenFlow Enable facility is a facility which is deployed in our university. It connects directly to our NREN, to Red Iris, which has given us much support for this. And the basic idea is that it supports the original Stanford paradigm, which is supporting experimentation and operation over the same infrastructure. That was something that was important for us because at a certain point we were running several projects which involved very different technologies. And for example, one of them was related to access networks, which uses the VLAN as a signaling, as a tagging method. So we were having problems if we used that VLAN tag for virtualizing the infrastructure. So we go further than layer 3 or VLAN tags for virtualization. And finally, we decided to go to our own experiment, our own virtualization or slicing method, which is the L2PNV, which is layer 2 prefix-based network virtualization. We also decide to have an authentication authorization scheme from the first time because of using that infrastructure for every experiment was a requirement. Well, just a quick view on this. This is already in the slide, so you can take a look at it. It is also published. Our idea is that part of the Ethernet address, what we call it a prefix, constitutes the slice identifier. So finally, we are able, by assigning MAC addresses, we are able to separate different slices for different experiments. This means, if we go further, this means that at a certain point, we take into account that in our case, half of the MAC address space is devoted to the slice identifier, and there was originally 1 bit in the MAC header, which gave the possibility to use local addressing schemes. So in fact, although at a certain time it was very difficult to get it published because reviewers didn't understand that. They thought that's hierarchic MAC addressing. No, it's not hierarchic, it's segmented, it's sliced. And well, we have, in order to have all the equipment linked to the network using a specific MAC address, you have two possibilities. One of them is assigning to the host a MAC address, which can be done manually, which could be at least not very easy and very error prone, or we can do this automatically, which is the preferred mechanism through a protocol we have already designed, which is the MAC address configuration protocol. In certain way, it's very related to the way the HCP is working, and in fact we have implemented this for Linux. It also could be done at the switch, but nowadays it's not an issue to change the MAC address. So what do we get? Finally, what we get is we give more possibility to the definition of the flows we manage into the experiment. If we were only using, for example, as tagging as in the flow visor, deciding on the first two layers, we should have less experiments or experiments involving less fields of the header. As soon as we rely only on the MAC addressing, we get from the VLAN up to the rest of the header to manage. This means that in our slicing, we can have several slices. In every slice, the IP addressing is independent. In every slice, the VLAN space can be used for every experiment. And there is also other additional benefits. It's that the management of the flow rules in order to take the decision on how to route the Ethernet frames is very simplified, because with a couple of rules, you are able to manage all the MAC addresses which are part of a slice. If you take a look at that, you can see that the number of rules increases with the traditional Ethernet or VLAN Ethernet scaling, but if we do our approach, the number of users per slice doesn't increment the number of rules in the flow table. I think it's put elsewhere. I think it's before. This was done, and this is currently running because the NEC switches we have a special firmware which allows this subnet or this MAC address, partial MAC address matching. So with new OpenFlow, it was done in OpenFlow 1.0. In newer version, this is also possible. But if somebody takes a look in detail, he will see, hey, these guys are using OpenFlow 1.0. I really don't know how they are able to do this. This is because we have a special firmware. The management also is very easy because it relies only on adding or removing prefixes. Well, this is a view of our infrastructure from the point of view of the slicing. This is quite a standard view, but you take into account, you notice that this box here doesn't appear in the slices. This is where the authorization scheme is enforced. You access to the slice through this function, but once you are inside the slice, this box disappears for you. Another additional benefit I didn't say before is the good thing with our Mac-based slicing mechanism is that the applications you design run on these slices unmodified. If you use the VLAN for doing the slicing, this finally at a certain point involves taking a look at the second VLAN tag instead of the outer one. So finally, this is interesting because once you have an slice, you take the stock application running on a plain OpenFlow slice, and it works, which doesn't work so easily with other approaches. So we have here several slices. This is the administrative slice, in which normally you are running only when you get into the infrastructure, and the slices are identified by the prefix of the MAC address. If we take a look at how the machines are deployed, this is perhaps not the latest infrastructure. This was the infrastructure we had when we presented this in GloveCon and in ONS. And just to take into account, we have 2 access switches, which are the switches that will enforce the access to the infrastructure. The rest of machines are there. We have several controllers. We have a special modified FlowVisor version, modified Basas, which is able to work with this MAC address scheme. And it's also interesting to note that the access controller and the admin controller are only used for the deployment of the slice and for the populating the access to the network. Once the slice is created, you are also given a slice controller which doesn't take into account any additional security checks, because only packets that are allowed in that slice will proceed. Just if anybody, I don't think this is a slide I took from Diego, who presented, just to remind you which is an FB, but I think it's not interesting to speak too much about that. But I would like to speak about the limitation of the software-defined networking in order to implement a network functionality. The basic problem with the SDN technology is that they have almost no concept of a state. I mean, basically, an OpenFlow switch is basically a stateless device. It's not able to maintain any state. How do we maintain the state? We maintain the state because we have an application on top of the controller which takes into account all the changes and is able to manage this state. Well, what does this mean? This means that if we want to take into account a state, much information must go up and back from the switch to the application. Well, how does NFB relate to SDN is also very, very clear. But from our point of view, it's very interesting as a way to support the SDN, to implement stateful solutions. Well, what does this mean? This means that at a certain time, we will be able to use SDN rule, a flow rule, to direct packets to the virtualized network function instead of relying on a tunneling mechanism to make them arrive. This is much more efficient. Well, this means that at a certain point we must also make some configuration steps. Well, we had 2 approaches. You can take a look at it. The first approach was try to do the access control virtual network function on the same equipment, having all the parts here. Which was the problem? The problem is that you had to maintain there an equipment, you have to do all the work there, and it had some problems with the speed. So finally, what we decided was to separate the 2 functionalities. We are able to manage the authentication arrive to the access controller. Once we decide this is a clear petition, we gave instruction to the SDN controller that will be install the flow rules to allow this client to proceed. So the state is maintained here, but all the switching and all the flow control is made at an OpenFlow switch at the OpenFlow speed. Okay, this is the general scheme. I think we will be taking a look at it. But basically, what you have is we have to provision the access, this first access switch, in order to allow only EAPOL traffic to go to the access controller virtualized network function. And we must configure some users. And once this arrive here, you get the correct authorization. You get the path set up in all the controllers, and you are provisioned a slice controller. And I think that at a certain point, the better is to try to make a demo. So just from the point of view of the software we have used, we have developed with libvirt and Zen. We have Apache MySQL and MRTG for the demonstration, and our modified flow visor. So John, if you're ready, now we're there to do the real. Okay.
Okay, so good morning, everyone. I just want to just put in practice what Eduardo has previously explained. I just want to show you how we have implemented this solution and how this could be, seems like a platform for developing SDN applications. We are using this platform at our research lab. We built this solution with our own resources, so this is not well, it's not there are no budget from other projects for building this. So there are some things that has been done just to do it work, but they are not so fancy, I guess. So first of all, what I have here is well, what Eduardo has mentioned. We are using a MAC address prefix in order to slice the network. For that, we have the NSE firmware in order to support this slicing mechanism. Well, what I am going to try to show here is how we can control the access to one of these slices. We are going to use this slice. So I'm just going to go into that slice. Once you have a slice, you can provision new resources to that slice. It's very easy. As I mentioned, the interface is not so fancy, but okay, we can put some clients, we can put some servers, we can just provision a way of controlling the access, that is the NFB machine that supports all the functionality in order to control the access to the network. Also configure and enforce at the edge of the network which flows are allowed to enter into the network. We can provision some controllers. Well, there are some resources that we can put in this slice. At this point, we have a demo client 1, we have a server 1, and we have this machine. This is based on host IP and free radius in order to implement the 800.2.1x. So one thing that we need to do here is, once a researcher wants to make a slice, he can provision some resources, and at a certain point he wants to control who researcher is able to access that slice. So for that, he can provide this resource, but at the end, he needs to configure that resource, which users are allowed to enter the slice and for what purposes. So we have here this configuration. We have a very basic tool to activate or deactivate this functionality. So at this point, this is provisioned, but it's not working. Okay. There is a very basic interface to provision users. At this point, we are using just one researcher with a password. It's very basic EIP implementation just to show that this is working. Then the services that are allowed for each of these researchers needs to be defined. At this point, we have two different services. We have an iPerf TCP server service, an iPerf UDP. I mean, we are providing TCP and UDP connectivity between the server. This is the MAC address of the server, IP packets. This is the source, and this is the destination, the protocol to distinguish between TCP and UDP. Okay, so these are the description of the services, and then we have applied those services to this user. Okay, so this user is able to request access for each of these services in a different time. Okay, so what I have here is, on the left side, I have the client. It's the same client, but different windows. Okay, so I have 3 windows for the client. And on the right-hand side, I have the server. Okay, so what I have here is the logs for this is the TCP iPerf, and this is the UDP iPerf log. So what I am going to do is, currently is not working, the authentication. So if I make a ping, this is working, so I can connect both. There is no control access enforcing in the access. So just by clicking here and activating this solution, this is not further working. It's just applying or not the forcing in the access. So if I deactivate, this is again working. Okay, this is just very basic. So what I am going to do is activate this control access. So, well, first of all, just to show that iPerf are working. So here is the log. In 10 seconds, we are going to have the output. So we have about 1 giga of bandwidth between the client and the server. If I launch, just put 500 megabits of UDP packets, I have the log, and this should also work. 10 seconds, we have the output. So more or less the 500 megabits that I requested. So what I'm going to do is activate this. This means that if I try to ping, or if I try to send the TCP iPerf, it's not working. It's not appearing here in the log. Okay, so this is not working. So what I am going to do right now is, if I ping, it's not working. What I am going to do right now is authenticate the traffic. We are using a very basic EAP MD5. It's not a security solution, but just to prove the concept. We are using the researcher with the profile for TCP traffic. So if I launch this, I am going to authenticate the user to get access to this kind of TCP traffic. So if I launch this again, this is working. And I'm going to have again the output. And this should work also about around 1 giga again. Okay. But if I try at this point, if I try the UDP traffic, this is not working. Because I only authenticate the TCP traffic. Okay, so this is not working. Yeah, did not receive. Yeah, so this is not working, and I don't have the log here. So what I am going to do right now is just authenticate the profile for UDP traffic. Success. So I don't know what happens, but no, this is not working. I don't know what was the problem. it seems that something is not properly working.
Well, that's the demo effect. One of the things I think is interesting to note is that the access from the same user can be to several different services. I mean, you only normally rely on one authentication for every service, so you must use templates, but here you have the possibility to really define services or to enroll for several services as you needed them. I think this is a quite different thing.
Yeah,
well, I don't know which is the problem, but anyway, I mean.
Yeah. Well, the idea is this, that we can request for a specific service at each time, and we have a platform in order for our researchers to configure specifically which researchers can access each of these services. So this is what we have developed here. Yeah.
Well, if you have any questions. Yes?
David from RNet, the other David. This overlaps very nicely with the problem we have within RNet, which is the concept of giving office staff or administrative staff access into secure networks. But we have a policy of not wanting to create classes or isolate users. Do you see this as being used as something that could go forward, and so I, as an administrator, can sit down and authenticate to the network and immediately get access to all the various things behind the network without having to use all sorts of firewall magic?
Yes, yes, yes. No problem about that. In fact, that's the good thing, and even you can have different. I mean, you can have whatever combination of you want. You can have one user, several services. You can do whatever you want, because every authentication process is unique, and you get additional rules in the access switch. From that point of view, I think it's perfect.
Kind of following along from that discussion, is it possible for a user to spoof themselves into a slice that you didn't want them into?
Well, here
if you can bypass the edge controller, that's the one that's your.
You have the same limitation that you have in .1x. I mean, if you put maxsec in the first jump, you are not able to spoof that. If you don't use maxsec, between authentications, you could enter the network. But this is no less than no more than you have actually.
Yeah, yeah.
The good thing is that you are not able, as in other solutions, to just changing your some parameter like VLAN. There are some implementation in which there is no enforcing on the VLAN. So. Okay. Any other question?
This is a very interesting presentation. So what we did was we also had some of the problems with FlowVisor that you were having as well, with it not scaling. So we rewrote it to basically we wrote a new tool to replace it, but essentially does the same thing, but it does a VLAN range approach. So you can actually define ranges as opposed to having to scale with a number of tags. Is that something that you could integrate into this as well? That style of approach?
Sorry, could you repeat the question?
So we rewrote FlowVisor.
Yes.
And what we did is we wanted to be able to support VLAN ranges.
Yes.
So basically you just get an entire VLAN range, and that does not have that scaling problem that you showed. Would that sort of functionality work as well, if you could do that?
Yeah.
But
yeah,
we did a different.
I can answer the question. The problem we also try to avoid is that the VLANs are exposed to the controller, because in that case the application that you are going to develop is aware of the VLANs.
Yes.
Unless you remove in the control plane, and this could be also done, but the application should be modified in order to tackle the VLANs. It's not transparent. One of the things that we put as a requirement is just to be completely transparent to the applications that are going to be developed for the controllers, because maybe you could get an application that is closed, and you cannot modify. So even the thing that you are going to develop in this scenario is going to run as the same in a scenario that you control all the switches. It's not affected the traffic. So end-to-end, the traffic is not modified at all, and all the control traffic that goes to the controller is transparent, as you see. And also another thing that is important is that at each time that you pick some traffic, you immediately know which slice is involved in that, because just with the prefix it's very easy to know this.
Thank you.
All right. Thank you very much, Eduardo.
Thank you.
They always say don't work with children, dogs, and SDN demos, don't they? Things never work out the way you expect. Okay, our second speaker, excuse me, is Dr. Tim Chown, who is from the... I should get an iPad, shouldn't I, really? From the University of Southampton, just over the sea from here. Amongst a wide range of interests, he is an investigator in the university's Academic Centre for Excellence for Cybersecurity Research, which is obviously a topic of much interest at the moment. I guess we should all thank him as well, because he's one of the original designers of EduRoam, which has been a fantastic thing for all of us, I think we'd agree. He's talking today about OFERTIE, enabling SDN OpenFlow support in ROIAs. Hand over to you. Thank you.
Okay, thank you very much. So today, where's the next? Have I got a clicker here somewhere? Is it this one? Ah, there we go. That's right. Thank you. So what I'd like to do today is just spend a few minutes just explaining what we've been doing in this project called OFERTIE. A large part of it has been exploring ways that application developers can write applications in a way that can take advantage of an underlying SDN-enabled network. So there's been a couple of main components of that I'll come on to. One is about developing that API, defining it, and working with some application developers to test how well it works. The other is developing the network control layer to enable that API to work through the control layer down to the underlying devices, which in our case are OpenFlow switches and an OpenFlow network. So there's a few names here on the first slide. It's myself from Southampton. There's I2CAT are involved as well. They've been doing a lot of the work in developing the control layer, which has been based on OpenNaaS. You'll hear a little bit more about that in the next talk. We've also got a booth out in the main corridors there, so in the few minutes that are left of the demonstrations you can go and have a look at that. The University of Munster have been developing their real-time framework, which you'll hear a bit more about in a moment, which gives an abstraction for an application to developer to manipulate objects in 3D worlds or in gaming environments. And by that abstraction, what we're trying to do is avoid the application developer having to use hardcore quas metrics, rather they express the requirements in terms of the objects and models that they're working with. And then the last person down there is Falco from Spinor. They're an application developer. They produce a package called Shark 3D, which is it's a world editor, and you can use it to collaboratively edit a 3D world, either for some advertisement or something that you're building that you want to show to people, or for a game, those type of applications. So that's kind of the setting. The project has been funded as one of the European Commission's FIRE projects. There's obviously a couple of dozen of these projects, or more than that over time, that have been running. We recently held a workshop, back in January, bringing together the different FIRE projects that have been working on SDN, and towards the back of the slides there's a link to that workshop and the PDFs there. But it's a very good community, and there's quite a few projects working in the SDN area, and again, some of the demos are outside there. So again, just to recap what I said at the start, what we're doing here is developing or exploring methods to allow real-time online interactive application developers to take advantage of an underlying SDN network. And that might be from the point of view of the consumers of the service, or it might be from the point of view of the content providers or the hosters of the service who may be in a data center. The project partners are involved. You've seen some of them on the first slide. So there's ourselves at the University of Southampton, Interroute as an ISP partner, I2CAT a research institute in Barcelona, Sobi, another application developer, game developer, and Spinor, who have the 3D world editor. So yeah, here's some screenshots of the type of things that they produce. Again, these types of editors can be used for different environments. And the two things we're focusing on with the two application developers we have, one is a collaborative real-time world editor. So the idea is there you're building some 3D world for some purpose, and you want to have multiple people editing it at the same time, and you want to have a good collaborative real-time experience while you're doing so. The other is a traditional, sort of classic, large-scale, massively multiplayer online game. And through working with those two application developers, we're getting, we believe, a good feel of the requirements and the type of interfaces they want to see. And the characteristics of these applications can be quite interesting. You might think they're quite predictable, but in fact, if you want to deliver the best experience both for the gamer and in terms of the delivery of the content, then there's a lot of variables that you have to deal with. And in fact, you know, even just with an online game, there's all sorts of different components and aspects of it, from distributing out very quickly updates to all players involved in an area. So they might be having some big battle or something, in which case they want to have all the updates delivered as quickly as possible to them. There may be quiet periods, they may be traveling through zones, in which case there isn't so much interactive traffic going on, and then the requirement drops somewhat. But then they might zone between different zones, and then they want a reasonable time in transferring from one zone to another as the state of their character is transferred from one zone to another, or from the server point of view, from one server to another. And part of this is figuring out, as more and more players come into a game and you want to scale up the game, you want to fork off essentially more instances of the servers supporting them, and then as the game gets quiet again, shrink down that capacity. So you're not over-provisioning the server-side capacity as well. So part of what we've been looking at, and you'll see this with the real-time framework, is how you can scale up and down the server side, and then in parallel with that, provision the network to those servers as they grow and shrink over time. So there's a lot of very sort of interesting quality of experience issues in terms of delivering these types of applications. So a number of challenges we've been looking at through the project. There's the sort of classic question of how, with a software-defined network, you can maximize the utilization of the network while also keeping to the SLAs that you've agreed as part of the provisioning of that network. We've also been looking at the different business models that exist for collaborative, the types of businesses that are developing massively multiplayer games and these types of world editors. Speaking to them about how they could potentially take advantage of SDN, whether that's purely within the data center and the hosting side, or, and you'd probably need inter-domain SDN provisioning for it, down through to the end consumers of those services. And the third very interesting question is, you know, how as an application developer, if you're writing one of these applications, how can you actually write it in such a way that the application can take advantage of that underlying network without you necessarily, although you could, explicitly dictate or specify what your quas metrics are. So that's what we've been looking at. In terms of the methodology, we've obviously been building some components here for the network control layer, the API. We're doing 2 phases of experiments. We're just at the end of the first phase of experiments at the moment, starting the second. And what we're doing in terms of facilities for this is reusing existing SDN deployments. So there was a previous project called Ophelia, and we're using the Ophelia testbed, but we're also looking at other infrastructures that we can apply this to as well. In terms of the technology being used, probably most of this will be very sort of familiar to most of you. And I think one of the interesting things is reusing OpenNaaS here as the sort of underlying method for doing the provisioning, but we've had to extend that to support the SLA side of the deployment. And you'll hear a little bit more about that in the next talk after me. So yeah, just one quick slide on OpenNaaS. This is a platform that's come out of previous projects. You may, if you were at TNC last year, remember they had a demo showing how OpenASA can be used to do virtualized CPEs, which is quite an interesting use case, but it's now being applied to various other areas as well. And what we've been doing in OFERTIE is developing OpenASA further to support things like network control layer, enhancements to do the SLA-based monitoring and control of the underlying network. So you can read more about that there. But again, you'll probably hear more about that in the next talk. In terms of the provisioning, it's the fairly sort of classic example of what you want to do. And in our case, this maps to having some kind of game service. You want some kind of API through which your game service can request certain quality of service that it needs, either in a direct way with classic quas metrics or in a more abstract way. And you want those metrics that you're putting forward, either directly or implicitly, to be used by the network controller and the SDN controller to provision your network to deliver what it is that you're requesting. So part of the solution to this jigsaw is coming up with, given all the constraints that are put into the controller or the network controller, figuring out the path computation so that you can deliver all the requirements you have, or as many as the requirements you have, through the network that you're controlling. And also part of that is sometimes you can't do that. So it's very important that if the application is putting in a request for a certain level of quas or a service, that if it can't have that, that it's notified about that and the application can react to that. So here's an example of the sort of, one of the examples rather, of a scenario that you'll find in real-time gaming. It's probably, I don't know how many of you here are avid gamers. Probably shouldn't ask you to put your hands up. There's a sort of a real-time loop here in terms of the interactions from the gamer to the service and back to the gamer again. So you want some network where the gamer or the interactive application user is interacting with the application. You want to prioritize to a certain extent the traffic to the server, such that arrives in a timely fashion. Most gamers will complain about unnecessary lag or latency when they're playing. But that can actually often be not necessarily the network between them and the server, but it can also be within the server itself. So there will be a certain amount of computation going on the server based on the inputs and the actions the players or the world editors are making, and the new state is being computed so that it can be then sent back to the players or the people that are doing the world editing. And the interesting thing there is that, as I said, a lot of the lag and the delays can be in the server side. So what we're doing in the project is using Munster's real-time framework, which I'll come into in a moment, to dynamically provision that server-side capacity. So as the number of players in the game go up, you scale up the server provisioning behind it. And of course, if you do that, you also want to make sure you provision the network to those services accordingly as well. So the real-time framework is essentially just a C or C++ library that's been developed at the University of Munster. And what it allows you to do is to abstract objects and entities in a 3D world and to model those. And it gives you certain functions that you can use within that library. For example, zoning. So in a map or in an area, you can have certain areas of the map that are each controlled by different servers, and as objects move between those, the servers communicate so that the objects can move between them. You have the concept of replication as well, so that if you have a lot of activity in a single area, you can distribute the processing of the objects in that area between multiple servers, even though those objects are in an overlapping area. That's a very useful function, particularly there'll be certain games where you get periodically very large-scale battles in a small area, and being able to do that type of distribution is actually very, very important. And then instancing is essentially where you have independent copies of the same area processed by distinct servers. One of the other things that RTF gives you, though, that's important from the point of view of the API, is it allows you to sort of have high-level views of what you're trying to do in terms of quality of service. So from the point of view of an application developer, they may be interested in the response time that a user gets for the application, but they're probably also just more interested in dealing with the number of entities or objects they have and where those objects are. And if you want to provision something in the network, an application developer there doesn't really want to say, well, I need this object to have this bandwidth or this throughput to here, or I need this particular QoS metric to apply through the network. What they want to say is, I need to zone this many objects of this size when they're serialized onto the network through this path. And if you can do that, then the application developer can just work with the objects that they're working with anyway without having to specify those metrics. And in a sort of a classic gaming environment, you can abstract the different type of operations you want to different classes. So, for example, there's the game updates or state synchronization where there's some battle going on and the players are moving around and the bullets are flying or whatever's happening. And there you want to get the updates of those changes out to all the players as quickly as possible. There's also then the state transfer or migration when you're moving player objects or other objects between different servers or different areas. And in that case, you want to communicate to the network control layer that you want a certain transfer of a certain number of objects to appear in a certain period of time. So from the application developer's point of view, you can say you want to move these objects over a certain period of time, or within, a certain period of time, and you punt that to the network control layer, and then it can use as part of its computation the fact that this has to happen in this certain period of time, mix that in obviously with all the other requirements that it has, do the path computation, and then apply the configuration to the underlying network to hopefully allow that to happen. And then you have the sort of bigger transfers, the sort of more large, what you call asset transfers. So those might be very large files, those might be new zones that a player's downloading as part of the game, or it might be new objects in the virtual world that you're building, and you want to get those through the network as well. So there's just different classes of objects. So this is just a screenshot of something called RTF demo. So just to get across the idea of what the real-time framework can do, there is a demo that the University of Munster have developed. I stopped short of trying to embed a video clip of this into the talk, because it's maybe a little bit ambitious here when I didn't have control of my own laptop. But if I was playing this, you would see all these little robot zombies moving around and shooting at each other. And it's highlighting the fact that even within a single area, you have different players in the area being controlled by different servers. So the ones in green are being controlled by one server, and the ones in sort of silver are being controlled by another. But it provides a seamless experience for the players, even though the services are running on multiple resources or multiple servers. And the important thing is to be able to scale that up and down as players come and go. So on to some thoughts about the API. We obviously had some design decisions to make with this. On the right there, you'll see a fairly classic sort of SDN architecture diagram. The control layer lying between the network layer with, in our case, the OpenFlow enabled devices, and above that, the application code, the code that the developer is writing, and the application code, call that the northbound API, and then the southbound API goes from the control layer down to the devices in the network. So the challenges here, what we were trying to do is to develop this northbound API for the application QoS, and to provide the option to abstract that away from the application developer having to provide specific QoS metrics to deliver that. And what we did in terms of the design was to split that into two parts. So there's an application level API where the application can speak to an SDN module, and the SDN module is integrated and can be integrated with the real-time framework. And then there's a network level API between that and the controller. So from the application developer's point of view, they're communicating to this module. The module's then doing the gathering of those requests, figuring out things like the path computation, and then applying those, applying the relevant configurations to the underlying network. And what are the elements of the network control layer? There's something called the SDN app, which is doing those QoS algorithms, tracking the resource allocation, giving the provisioning commands down to the underlying network. There's the monitoring tools. So this is where we're checking that the requests are being honored, and that there aren't underlying changes in the network where the SLA, for example, is being broken. And then we can, if that is happening, then we can indicate that back to the application, because the application can be running a listener looking for any messages coming back from the SDN app that are indicating that the quals situation has changed and the application can no longer be granted the quality of service that it requires, and the application can choose how it's going to react to that. And then there's the controller part, which is doing the implementing of the paths. And all this is based on, of course, OpenFlow is the fairly standard southbound technology, and as I said earlier, on OpenASA for the NCL itself. So again, you'll hear more about OpenASA in a moment. A little bit more detail inside the network control layer. So again, the applications on the top. Underneath that, we have the three elements that I just explained, the SDN app, the monitor, and the controller. And it's the controller that's talking southbound, and the SDN app that's talking northbound there. So here's just some very, very sort of simple sort of excerpts of sort of code that you could use in an application here. So it just gives you an idea of what the application API might look like if you're expressing a quals requirement directly in this case, rather than in an abstract way. And similarly, your code can also listen for messages coming back from the controller to indicate that there may be some issue that you have to react to. As I said at the start, we have a couple of application developers on the project. There's Sobi and there's Spinor. The Spinor have the Shark 3D virtual world engine. So what we've had Spinor do is to work with Munster to port their code so it's using the new API that we've defined through RTF into the network control layer. And they've been able to successfully do that, and we now have a demonstrator. That's not what actually is on show at the booth here, but we have a demonstrator where all that's being used for multiple people to collaboratively edit a 3D world over the Ophelia testbed. So a little bit about the experiments we have been doing. This has all been running over the Chown network, and we've been using the Ophelia testbed. More about that at the moment. Ophelia is essentially it's been built through a previous project. There's an Ophelia control framework through which you can provision an SDN network. There's multiple sites around Europe. It's also being extended to Brazil and Japan with further commission-funded projects. So we're using a small number of islands on this testbed to do our experiments for the applications and the hosting side of things. Right, yeah. So that's just a little diagram there showing you the extent of where Ophelia runs to at the moment. So the original site's in Europe, and it's also now being extended to Brazil. So that's the fiber project, and to Japan, the Felix project. And I think there's a fiber demonstration booth up in the demo area that you can go and see probably still for a little while. One of the interesting things with Ophelia, though, is that it's a project that finished in September 2013. So we've been building on the Ophelia framework with our modifications to OpenASA and the new APIs on the assumption that we can continue to use the Ophelia testbed. That's proved a little bit problematic in some ways. Obviously, once a funded project ends, there isn't so much incentive for the islands and the facilities to remain. However, Ophelia is now, or the project has formed this Ophelia Foundation as a means to provide some sustainability to the testbed. So that's been very useful for us in terms of being able to keep that work going. I did mention at the start we've been doing some business use cases and some business analysis of the application area, so the massively multiplayer online games and the real-time world collaborative editing. I won't go into the details of those here. We do have deliverables on our website that detail that business analysis, so if you're interested in that type of thing, you could look at those. What experiments are we doing? Well, the ones that are just completing, there's the dynamic quals for both the massively multiplayer games and for the Shark 3D engine with the API that Spinor have been working with Munster. We've been testing the network monitoring and the SLA violation reporting. Those are the new elements in OpenASA that are now available as part of the OpenASA is an open source package you can just download and use. So all that stuff's been integrated into the production release of that. Further tests with Shark 3D. We've been looking at extending the test. Initially, the tests were just running on individual islands of Ophelia, but we were in phase 1 making sure that we could do the tests with the provision slices over multiple islands. And then the last thing there, one of the things with Ophelia is it's based on a control framework which uses the flow visor, which is limited to OpenFlow 1.0. So we've been doing additional tests outside the scope of Ophelia with OpenFlow 1.3 in particular, so that we could do with tests with both IPv6 and multicast, both of which are very relevant to the application areas that we're looking at. And in terms of the tests we're going to do moving forward, there's the SDN managed voice over IP that Interroute are going to bring to us. There's multi-domain QoS management for video on demand. There's further development of the Shark 3D and RTF integration. There's tests we're going to do, hopefully across Janet with IPv6. That'll involve the University of Bristol and their resources there. And then an inter-testbed experiment, hopefully, where we're looking to work with another framework. And just to close up, just some reflections on some of the things we've learned and some of the sort of questions maybe for the community here. I think one of the first things, obviously the classic problems we have is how to handle multi-domain SDN paths. That problem has been described in many talks this week and in the demo that SurfNet did, for example. So most of the things that are happening with SDN are provisioning in a single domain. So that might be a data center, it might be a campus. What we're doing in OFERTIE is exploring the inter-controller or inter-network control layer communication, the sort of east-west interface, but we're doing that in a relatively simplistic way. For example, we now have no authentication there. We're just looking at how the messaging would work, how the provisioning could happen to enable end-to-end SDN. I think it's also important whenever you do a project like this and you're sort of in your own little bubble of, in our case, Ophelia and OpenNaaS, etc., to figure out how the lessons that we've learned and the technology we've used are applicable to other frameworks and other environments. So, for example, as I just said, Ophelia is limited to OpenFlow 1.0. We want to be able to demonstrate this, or to take the lessons we've learned to other frameworks and to ones certainly that support more than 1.0. So, for example, the new Open Daylight framework, again, that was demoed in the halls upstairs earlier this week. What can we do in terms of migrating what we've done in our area to Open Daylight, for example? And I think OpenASA is being used to some extent within Open Daylight too. And then finally, how appropriate is the API? So we'd like to speak to more application developers that can look at more details of the API and see how it feels to them. We've obviously only been doing this with the 2 project partners we have in the project at the moment. We'd very much like to speak to other application developers. And a couple of other quick thoughts. One is on the provisions of testbeds itself. This problem has been, again, raised in other talks this week. Building on Ophelia, building on an existing project, we do have the problem that project is finished. So it's very important to get some kind of sustainability in testbed projects. So in the fire area, you have research projects and you have sort of facility/testbed projects. And for some people, the interesting research is building the testbeds. And then when that project's finished, they just want to move on to the new, greater, better testbed. But sort of running along behind them are other research projects that want to use those testbeds. So it's a bit of a shifting sand problem. And we need to think of ways of allowing those research projects to have some continuity of expectation of the testbeds under them. So perhaps we need to think about that. So one of the ways this is being solved is with this foundation concept. So Bonfire are doing that. Ophelia are now doing that. So it's an agreement between the partners to continue some level of support for that framework or their testbed for a period of time at a very minimal level. But maybe in the European funding model, they should ensure that projects that are testbed projects, they might have a 2-year fully funded project, but then ensure that for maybe 3 or maybe the 4th year, they have a very minimal level of funding and a guarantee to continue to provision that testbed for a period of time. And there are other projects here, again, being demonstrated. Alien is another project up in the demo area. They require Ophelia for what they're doing. And then finally, on testbed connectivity, how can we provide layer 2 testbed paths in a fairly dynamic way? Again, this has been mentioned before this week. At the Géant level, you have had services like Autobahn. You may have heard of the new Testbed as a service. Those are great, but generally either between Géant POPs or certainly limited to the Chown points of presence. Within the NRENs, there's different ways that NRENs can provision layer 2 for you. So in Janet here, they can provide MPLS-based layer 2 paths if you want to do experimentation. And then you've also got to remember, again, as someone said earlier in the week, the provisioning within the campus, within the site. How does that happen? And all this can happen, it just takes time. And it would be really good if these types of things could be provisioned more dynamically, almost on request. And I think that's something we really need to work towards. And of course, the lessons in provisioning the testbed also apply to provisioning SDN itself. So that's it. There's a website you can look at more information about the project. There's a number of deliverables there, the European Commission style deliverables. They're quite long, as we're required to deliver. We're also producing some shorter, more digestible white papers, and there's various other things up there. The other thing that's really useful to look at in terms of getting a feel for what's happening in the FIRE-funded area in terms of SDN is that workshop that I mentioned that happened in the end of January, I think it was. There's 15 or 20 presentations there from all the projects doing something SDN related. And we're planning to do another workshop in September, so keep an eye out for an announcement of that. And if you're doing SDN work, we'd love to see you there. Okay, thank you.
That's great. We've got time for one question, I think, maybe. Any questions? Maybe I'll steal it then, as the other David from ARNet. I really like the fact that you've got robot zombies in your talk. That's very important.
In the graveyard slot.
If you're rolling this out to gamers to be able to reach central set of servers, I guess they might be a LAN party, but it more likely would be across an ISP network. Does this involve big changes to the ISP's network, like just around the edge or right across the core to support SDN?
Yeah, so... Sorry, just standing in the microphone. Yeah, so obviously in that case you're going to need multi-domain SDN of some form to be deployed, which is obviously a challenge for the future. But equally, this type of technology could be used, for example, within a single campus or within a single data center. So essentially at the moment we appreciate that most of SDN is just happening within a single domain, but I think this is just showing a vision of how we could potentially ultimately have value-added services for gamers. So at the moment, for example, a lot of games have gone free to play. This is part of the business model deliverables we have. A lot of games have gone free to play, but a lot of gamers are also very happy to pay quite surprisingly large amounts of money to get an edge over the people they're playing against. So value-added services where you can offer a gamer that extra bit of guarantee of latency for a little bit of money. There's quite a lot of proof that they'll be happy to pay that. But it does obviously require the ISPs to be deploying the supporting technology for that. But I think there's definitely a model there, and I think we're sort of showing how things could be, but obviously it's up to the ISPs to work with the other domains to allow that to happen.
Thank you very much.
Okay, thank you.
I'll invite our third speaker for the day to come up. I'll introduce you to Jordi Ferrer Riera, who is a research engineer at i2CAT, who's just had a mention, I guess. It's neatly put together. Jordi joined i2CAT in the Network Technologies cluster in 2007, and has worked on various EU-funded projects, including Manticore, Phosphorus, and one in particular I'll note, which is the Glyph generic network interface tech group. And I mention that because I'd invite all of you to come to Queenstown at the end of this year to the Glyph meeting in New Zealand on behalf of my cousins at Rian's, and feel free to drop by Australia on the way. And Jordi's a PhD candidate currently at the Telematics Engineering Department of the Technical University of Catalonia, and he's going to talk to us about OpenNaaS, an enabler to deploy virtual network functions. Over to you.
Okay, thank you, David, for the introduction, and thank you all of you for staying until the very last session of the conference. Okay, I know that we are a couple of minutes late, so I will try to be on a schedule. Okay, so as David said, my name is Jordi Ferrer. I'm from the i2CAT Foundation, and I'm going to talk about OpenNaaS as an enabler to deploy virtual network functions. I'm pretty sure that you have been listening about Open Network as a Service for the whole conference, because it has been present in several presentations and also in the booth that we have. And first, although you only see me here speaking, the work that I will be presenting is a collaborative work mainly between between all my colleagues at the I2CAD Foundation, so Josep, Jose, Eduardo, and all, the OpenNaaS development team, and also the OpenNaaS community. Okay, basically the outline of the presentation is quite simple. So first, some words on the introduction and the rationale of the OpenNaaS and the network as a service. Then we will go to the concept of network as a service and the Open Network as a Service framework as the first implementation of this concept. Then I will present some use cases or some specific deployments and implementations that we have with the OpenNaaS framework, and then just the conclusion to close the talk. Okay, so first let's start with introduction. I would, okay, how many of you in the audience are familiar with any of these sentences? Yeah, most probably, well, it should be all of you, because these sentences are extracted from other papers, from session description, and from other talks in the conference. And if you take a look, you will have that you have deployment of SDN networks, SDN capabilities, network functions virtualization, integration of network and IT or network management system and IT management system. We have network as a service, we have virtualization, and we have significant interest in the community. And these sentences or these quotations are the clear example of it. But if we take a look backwards or behind on what it has happened before all of this, and this relates to the first talk that Brian from HCINet provided about managing different networks. We have that the network administrator, when he holds or he owns only a network of 1 or 2 or even 10 devices, he can manage them manually without any problem. But as long as the network becomes huge, let's say, and there are, or it is populated with different heterogeneous devices, it becomes impossible to manage this kind of different devices. So this is why we deploy the different network management systems to facilitate all the management and all the control of the different devices. And once that we had the management systems in place, one started to think, okay, but we are not using efficiently these resources. We need to enhance or improve the efficiency in the usage of the resources. So this is why we decided, or we started to deploy or to implement the virtualization layer, right? So we were virtualizing the different resources. We were sharing these virtual instances among different users, trying to improve the efficiency and in the usage of the different devices, right? So basically, the virtualization layer was responsible to build uniform virtual resources and offer them to the end users, to other operators, so they can provide services on top of them. Once that we have these virtual resources or these virtual infrastructures, what we had is that, okay, we need to control them. So you are virtualizing the infrastructure, but once that it is virtualized, you need to configure, you need to control these virtual resources, because you want to provide services that are constantly changing. And we started deploying, well, we had the control planes or whatever on top of these virtual infrastructures. And what is happening nowadays is that we are going one step beyond. We are saying, okay, these control and management functions can be also virtualized on top of these virtual infrastructures. And this is what nowadays is called network functions virtualization. So we are building virtual network functions, and what happens is that the different network devices, so the logic and the intelligence of the network devices is going, or is being extracted and inserted in the control layer. And this is mainly the network functions virtualization approach or trend that was started by the European Telecommunication Standard Institute, so the ETSI, and it started, I would say that 1.5 years ago, so it is quite new. Although everyone is talking about them, it is quite a new approach. And basically it consists in the externalization of the specific network functions from the hardware devices, so from the network devices, into a standard server, so into virtual machines, let's say. And what the ETSI NFB standardization group is claiming is that you can implement any network function, firewalls, even authentication, as Eduardo was presenting in the first slide, into any server. This way, you can, let's say, enhance or improve the management of the different network functions. So you can migrate using the VM migration. If you had one firewall or if you had the access control, you can migrate them easily, you can replicate, or you can instantiate on demand. And the key benefits that the standardization group is claiming is that you have obviously reduced costs, so you do not have to invest as much, well, so many in the different or specific hardware devices. You have you facilitate the operation, you enhance the reuse of existing infrastructures that you have in your data center, and etc. Let's say. But if you take a deep look on the documents that the standardization group is creating, you will find, and this is in the architectural reference document that they are providing, you will find this sentence. So the actual management of the virtual network functions is out of scope of this NFB architecture. And if you remember in the first slide where I was saying that the network administrator is not able to manage a lot of different network devices and so on, I consider myself still to be young, but we are going in the same direction if we are letting out the management of the virtual network functions of the pictures. So mainly this is the point where we believe that the network as a service model and the OpenNaaS framework in detail can, let's say, join the game as the manager or as the let's say, virtual network function management system. And again, using another quotation from this conference, this is the advantage of being in the last session, is that Dave Wilson yesterday was talking about the network as a service for the for the network as a service model, and he was saying that we see network as a service as the way to implement those solutions, to prototype them. And he was talking about complex services, complex network services that cannot be efficiently deployed. So if you think, or if we think in network service as a virtual network function, because at the end the function is providing a service, or even a composition or a concatenation or a chain of virtual network functions as a way to provide network services, we can extrapolate this sentence to say that, yes, we see the network as a service model as a way to prototype or to implement this kind of virtual network functions enabled solutions, right? So what is the network as a service? I'll go very quickly through these slides because most probably you have listened about it. So the network as a service is defined as a service delivery model, which would be analogous to the infrastructure as a service for the IT realm, that is used for providing dynamic, scalable, secure, and isolated network access for multiple tenants. Okay? So mainly it's related to the network infrastructure provisioning workflows. So through the network as a service, you can define and you can build all the provisioning workflows for any kind of network. It is also related at the for the enabling dynamic and scalable network services, even if this service is a simple service, a complex service composed of one or several virtual network functions. It is also related at the multiple tenants accessing this network service. For example, if you think in the pure infrastructure as a service service, meaning that you are providing the network, virtual slice of the network as a service, you need to ensure that multiple tenants or multiple users will receive different slices. And obviously, you need to keep this network service secure and isolated, right? The basic cornerstones of the network as a service model or service delivery model that we are defining is that it provides the decoupled network resource management and control from the actual services delivered, meaning that it is the coupling the infrastructure and management from the services that are provided on top of this infrastructure. It also provides an abstracted set of the management functions at the service stratum. So, since we are decoupling the infrastructure itself from the service where we are, that it is being provided on top of this infrastructure, the NaaS should provide also a set of abstracted management functions for the service layer. Obviously, we need also coordination between the two layers or between the different layers in order to provide and to control the services. And obviously, since we are in a multi-provider, multi-user, multi-tenant environment, we need also to manage somehow the access to the different resources. So it has to be a policed resource managed access, depending on different access rights and ownership patterns that are defined in the NaaS, let's say, model. Okay, and this is, or considering this, we firmly believe that this service delivery model confers or holds the enough flexibility and elasticity to provide support to all the implementations related to SDN and NFB. I'll go later on detail on the actual implementations that we are currently making with this NaaS model. Okay, and now once that we have the basis of the model, we go to the real implementations, and here is where this Open Network as a Service framework comes in. I would like to ask, but I think I know the answer is that how many of you in the audience are familiar with the Open Network as a Service framework? Okay. Okay, Tim has presented before, so it should be every one of you raising your hand. Okay. So basically, what the Open Network as a Service framework is first, it's an open source framework that it's being used, or it was created in order to manage physical and virtual networks. It aims also to virtualize different network resources, heterogeneous network resources, whether they are layer 3 routers, optical switches, or even full networks. So you can virtualize, you can manage an IP network, a virtual network. It is also used or aims at deploying dynamic network infrastructures. As I said, supports heterogeneous network devices and also provides access to different tenants, different providers, and different users. Mainly, as a summary, it offers, so it implements the network as a service model that I was talking before. What is the value that OpenNaaS provides? So if you want to use an open source framework, a framework implementing the network as a service concept, why would you choose, or what added value provides to you the OpenNaaS framework? First, is a robust and extensible open source framework. I really encourage you, also Tim already did, to go to the website, look at the documentation, download the source code, and participate in the community. Then it offers the network as a service model for operation, maintenance, and provisioning of different network infrastructures, different network services, and different virtual network functions. And also it provides recursive delegation of access rights over the different resources. So mainly the different resources that are within the framework are shared or are delegated between different tenants, between different users of the framework. So the access rights are recursively delegated between different. So OpenNaaS holds a way to define the different access policy for the resources. And then, and this is very important, how OpenNaaS works, or what is the main idea, is that it works with a lightweighted abstracted operational model. So it mainly, this is what we call the hardware abstraction layer. I think that yesterday was also a presentation about hardware abstraction layer. It's the same name, but it's not the same thing. So don't get confused with this. Basically, in OpenNaaS, what we have is that any resource is no longer represented, so any device, sorry, is no longer represented as a specific device, but it is represented as an abstracted resource. And on top of this resource, on this software entity, what we have is that we built a set of capabilities. So for example, if you have an optical switch, the abstracted model will be obviously vendor agnostic, and on top of it there will be several capabilities, being the optical switching capability the most important for this resource or for this device. Basically, this model is flexible enough to accommodate different designs, as we will see later on, and it's fixed enough so common tools can be built and can be reused between the different resources. Okay, and then, well, it allows the creation of virtual representations of physical resources and also the virtualization through a slicing or even aggregation. When we say that we are building a whole IP network, for example, or a whole network as a resource, we are providing this virtualization through aggregation, right? This is the architecture, and again, I'm pretty sure that you have seen this picture in several presentations. It's a layered architecture. We have here the base layer where, let's say, that the base layer that is the core or the technological layer of the framework. So this is common for all the bundles and all the deployments, and hold some basic functions such as persistence, queuing, or management of the software resources. Then we have the network as a service layer, that is where the abstracted models live, and where the capabilities are defined. So mainly the capabilities are accessible through our remote APIs. And then we have the network intelligence layer, that is where you build your own applications, your own network functions, your advanced control functions. Okay, in detail, we have here the platform layer. As I said, it holds all the reusable building blocks that are common to all the different bundles and all the extensions, sorry. And mainly it controls the access to the different infrastructure resources that are considered. Then we have the network as a service layer. Okay, this is let's say the most important layer in I2CAD, because it's where you build all the resources that are managed by the framework. And as I said, you define the resource as a generic resource, and you associate a set of capabilities to each resource. And these capabilities are accessible with the remote APIs. Mainly we have REST APIs, but you can develop your own remote APIs if REST is not compliant with your requirements. And these APIs are used by the network intelligence layer, by the components in the network intelligence layer. That, for example, at the moment we have that it is integrated with some cloud managers such as OpenStack, or even with remote management user interface, graphical user interfaces. Sorry. Okay. Now let's move to the. Okay, you have the basis of the framework, and now let's move to the actual deployments and actual or real use cases on where we are using the OpenNaaS framework. First is the ECA-net virtual CPE that was presented again by Dave Wilson yesterday in the session. So I will not go into the details, but mainly the OpenNaaS framework is used to implement and to deploy the virtual CPE. This is the interface configuration and management for the virtual CPE, so you can configure the virtual CPE depending on your needs. And then we have a really useful use case over an SDN, over an OpenFlow network that we virtualized the routing function, right? So mainly we had an OpenFlow network based on this this topology, and what we are doing is we are modifying the controller. It was the floodlight controller, and the routing function was externalized and deployed in OpenNaaS. So it was implemented through OpenNaaS. We have the function in the network intelligence layer, and through this, let's say through this externalization or virtualization of the routing function, what we did is try to separate the IPv4 and IPv6 routing traffic. So we had one machine that was responsible for routing the IPv4 packets, and we had another machine that was responsible for routing the IPv6 packets in the network. We just, let's say, we just implemented communication through web service between the different controllers and the OpenNaaS framework. And whenever there was a packet that the controller didn't know where to route it, where to send it, it was using the web service to ask OpenNaaS, hey, where should I send this packet? And OpenNaaS had a routing table model, and it was accessible through a management user interface, and you can configure, you can manage your network. We implemented two methodologies, the proactive routing and the reactive routing. And if you came at the booth, that team was presenting, the OFERTIE and OpenNaaS booth was presenting in the talk before. We have this demo set up. So we have two domains, one OpenFlow domain at PSNC in Poland, one OpenFlow domain at I2CAT in Spain, Barcelona, one controlled by Open Daylight and the other one controlled by Floodlight. And what we do is we manage the forwarding function, the routing function between the two domains, right? So we avoid the switches sending ARP messages between them, and the controllers talk or communicate with OpenNaaS. Another use case is the data center automated management. This is a very significant also use case that we had, and we are also providing some demos, one colleague of mine in the booth. So the idea was that Sursara had several requirements and wanted to develop and implement a vendor-independent overlay platform on their data center. And what they wanted was a unified way to configure the different networking resources in an easy to deploy, easy to configure, and easy to manage solution. Right? This is what everybody wants. Okay. And well, mainly they used OpenNaaS for managing the different and heterogeneous network resources. This is another demo that we have, another deployment that we have jointly with ADVA and Eurotech. And this has been done in the demo corner the day before yesterday and yesterday, and this was very impressive because ADVA, they have their own optical ring, so they had a rack of optical devices, reconfigurable optical add and drop multiplexers on their booth, and Eurotech has an encoder on the other booth, and we have OpenNaaS in our booth. And what we are doing is that OpenNaaS is using the hypervisor of ADVA to abstract the OpenFlow network and configuring them as a function of the encoder of Eurotech. So whenever the encoder wants to transmit video, sends a message to OpenNaaS, and OpenNaaS is responsible for managing all the network, right? And if you come at the booth, you will see that the video is running successfully. Finally, well, I will not go into details of this demo because this demonstration is the OFERTIE one that has been presented by Tim previously, and basically is the network control layer that he was talking that automatically detects the congestion and is responsible through Floodlight to configure the OpenFlow network. And okay, since we are building an open source framework, what it is important is the community behind the framework. So we have here the founding members of the OpenNaaS project or framework that was built in the Manticore project that ended more than 1 year ago. So the framework is self-sustained for more than 1 year, and currently this community is growing. We have that several, 2 tasks in Chown are using OpenNaaS for their developments, as have been presented yesterday by Dave and Eduardo. But not only Chown, we have, or OpenNaaS is being used in several FP7 funded projects, such as the content project, where we have heterogeneous infrastructure composed of wireless and wired testbeds or domains. So we are somehow converging wireless and wired testbeds through OpenNaaS. The Shifi project, where OpenNaaS is the orchestrator of different future internet infrastructures. We also have 2 more projects, the Sodales one that focuses on the access segment of the network. They provide a novel active remote node in the access, and we are using OpenNaaS to provide virtual slices and provide control on these virtual slices over this access infrastructure. We have the OFERTIE project with the network control layer that has been presented. And most important, we have you as members of the community. Join the website, download the code. Please consider that for creating the ultimate network as a service experience, it's not required to just develop code. You can join the community, you can give us new requirements, you can propose new use cases, you can criticize the framework, and whatever you want. This is why we have built the open source community. Finally, last words, because I think I'm out of time. Okay. So what we can say to close up is that SDN and NFB are here to stay, that for sure. There are many potential benefits envisaged adopting these kind of solutions. And what we say, or what we claim, and what we really believe is that the network as a service model that has been widely presented and talked at the Terena conferences for more this year and last year, and I would say that even 2 years ago, it holds enough elasticity and flexibility, both business and technological part, to support these SDN and NFB new deployments. And finally, you have seen that the Open Network as a Service framework is being used. It's being extended, the community is growing, and it should grow even more in the coming months or the coming years. Okay, so that's all. One last thing is that you will have in the coffee break now, the last coffee break, so the last opportunity to come to our booth. Both will be Tim, myself, my colleagues will be there, so if you want more details, you are more than welcome. That's all.
Thank you, Jordi. That was fantastic. We got time for one question. Anyone? We're not going to let him off that easy, are we? Actually, I don't have a question. I have a comment, I suppose, which was just I really like the sustainability that you're working on. You know, many projects come and go, but having something that continues is really important. Thanks again, Jordi.
Thanks to you, David. Thank you.
So before you run off, a couple of announcements, which are maybe important because this is the last day. As Jordi said, there are demonstrations still on out during